it's that time of the year to look at collisions. And, we can study carts colliding, different collisions that are, fairly simple, but can get complicated also at the same time. And the best thing is to be able to make a model, a numerical model of collisions. So I'm going to show you the super simplest ever possible numerical model for collisions. So if I want to have a collision between two objects A and B, and I want to show that momentum is conserved, and I want to look at kinetic energy, what's the most important thing? When is momentum conserved? Well, if I take my system of A and B, object A and B, then I can apply the net force, the momentum principle, to the system. So in this case, my system has no external forces acting on it, so F net is 0. If F net is 0, then delta P has to be 0 for the system. That means that the momentum before the collision has to be equal to the momentum after the collision, where that's the sum of these two momentums. So as long as I do that, as long as I have no net external forces, I'm good. And one way to do that is to make sure that I only have internal forces. So if I have mass A pushing on mass B, then I have to have A pushing back on B. B on A and A on B. I have to have the two forces. I have to have the two pairs of forces. So if I calculate some force, and it doesn't matter what this force is, as long as this force is equal and opposite to that force, then momentum will be conserved. And we can make a cool collision. Now, I could just have a constant force. I could just say, F equals, I'm just trying to think, 2 newtons in the x direction. Or, yeah, I could do that as long as this one has 2 newtons in the negative x direction. It doesn't matter. But if I want to make it look like a collision, I need something. I want to have two things I want to be true. I want to have this force between them. I want two things. One, I want it to be in the direction of R. Where R is a vector from A to B. I want it to be in that direction, so it's a central force. That's because imagine these two things were actually colliding. They would push each other apart in the direction between their centers. And then I want it to be short range. And by that I mean when they're far apart, I want the force to be essentially 0. Not actually 0. It doesn't have to be actually 0. Just almost 0. Okay. So I'm going to make the following model for my force. I'm going to say the force on B, FA on B, is going to be equal to, I'm going to write this as A R hat over, I know you're thinking, what the heck, R cubed. So, and where A is just some constant, I'm going to change that. Let's say 0.001. I don't know how big it should be. I'm just going to pick. And R hat is the unit vector in the direction. R is the vector from A to B. And then I'm going to cube it. Why am I going to cube it? Because if I have 1 over R cubed, when R is very large, this number is very, very close to 0. When it's very, very close, when R gets very, very small, this number is very, very large. This force is very, very large. So let's see if we can make this fake collision and make it look real and adjust the parameters. So I've already got a program started in Python, and I will give you the code. But let's just jump over here and start playing with some code. So I have two balls. I have ball A and I have ball B. Move my chair. I feel like my chair's not in the right spot. There. Okay. So they're just spheres. I'm going to make this bigger in just a second. So these are my two masses. Let's go over here and make this much bigger. That's good. I like that. So I made my spheres. I gave them a position. I gave them a size. It doesn't really matter. I gave them both the same mass, 100 grams. I'm just picking stuff. I gave them both a momentum. So ball A is moving towards ball B. And I can model that, right? So, but now all I want to do really is to, for numerical calculation, calculate the force between them, use that to update the momentum, use that momentum to update the position. And then we're going to make graphs. So I've done this a bunch of times. Let's just get right to it. So the first thing I'm going to do is say A is 0.001. That's my coefficient for the force. And then I'm going to say T is 0, dt is 0.001. So we'll run in real time. And let's run this for 5 seconds. So I'll say while t less than 5, rate 1000. So if you're not familiar, rate 1000 tells web v Python, hey, don't do more than 1000 loops per second with a time step of 0.001. That'd be real time. Okay. So the first thing I want to do is to calculate that vector r, because I need that to calculate my force. So I'm going to say r is, I said it was b.pos minus a.pos. I said it was going from a to b, right? And so that's final minus initial. That's that. And so if I have, just a quick reminder, if I have an object A as a sphere, its POS function, its position function, is its vector position. So I can use that. Next, I'm going to go ahead and calculate the force. I'm going to call this FAB. It's the force on B due to A. So it's A pushing on B. And it's going to be equal to A times norm R divided by mag R cubed, just like I said. So it's that constant A. Norm R is that unit vector in the direction of R. I need that, right? Because if I don't have that, then I have the magnitude of R. And it's just a scalar value. I need a vector force. And you can play around with whatever force you want. You can make whatever calculation you want. Okay, now let me get some space here. Next thing I want to do is to use that force to update the momentum of mass B. So I can say B dot P, the momentum, is equal to B dot P plus FAB times dt. That is the momentum principle right there. A little bit bigger. That's better. Next, I need to update the momentum of mass A. So A dot P equals A dot P minus FAB times dt. So I don't really need to recalculate a new force. I don't need to calculate FBA because it's just equal and opposite of FAB. And this is why momentum is conserved, because these two have plus and minus right there of the same force. That's key. Now I'm going to update the position. I can do it either way. B dot POS is B dot POS plus B dot P times dt divided by B dot M. So this dot stuff, just so you know, I mean, it's very, once you start dealing with multiple objects, you always want to assign properties of an object. So instead of saying M1, M2, M3, I'm going to just associate that with the object. Trust me, it works out much better. A.POS plus A.P times dt divided by A.M. Now I just need to update time. T equals T plus dt. I think we're ready. Let's run this thing and see what happens. It might blow up. Sometimes I get a minus sign wrong, but we can figure that out. It still should be conserved, though. Oh, I got something else wrong. Cannot subtract a scalar and a vector. Well, that's true. Well, I didn't do that. Where did I subtract a scalar and a vector? R, B.POS, that's a vector. That's a vector. 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 Let's just try this. Print FAB. I made some error. It didn't print FAB, so it didn't get to that line. We're doing some bonus troubleshooting here. Okay, so it didn't get there. Let's print R. I think R should be fine. Didn't do that. Okay. So it didn't even get to the print statement. So that's not where the error is. Oh, haha. I know what I did. Okay. So let's call this constant C. That's what I did. So so one of the nice things and bad things about Python is that I can use the same name and make it something completely different. And Python's like, you do whatever you want, man. It's your code. So I had A as a sphere, and then I told A as a constant, and that's not cool. Okay. Lesson learned. Here we go. Collision time. Okay, so you'll notice that one is moving a little slow. Let's make it move a little faster. But this is exactly what should happen. If I have a collision between two equal mass things and it's elastic, one should stop and the other should go. And so let's run this for, this is running a little bit faster. Let's say 0.6, twice as fast. You know that they don't actually touch, but momentum is conserved. Now, if I want to make it look like it gets even closer, I can do that. Let's make this coefficient a little bit smaller. What if I make that smaller? Then the force is going to be less. It's going to allow them to get closer together, and it's going to be a shorter range force. And they actually touch, right? They're not real objects. I want that to be not quite touchy, so let's make that a little bit bigger. 3. I'm just picking some values here. Okay, I'm pretty happy with that. But let's check. Is momentum conserved? Is kinetic energy conserved? So we need to calculate that. So let's add a graph. I could just calculate the momentum before and after, but that's no fun. So graph G1 is graph. X title is time. I'll just put T. Y title is momentum. I'll just put P. Width equals 500. Height equals 200. I'm going to do 200 because I want to make 2 graphs. So I'm going to plot the x momentum of A, the x momentum of B, and the total x momentum. So I'm going to say FAP is G curve. Color equals color dot red. FABP equals G curve. That's the momentum. Color is color dot blue. I'm not going to put labels on these, but you could. And then I'll say FTP, the total, is G curve. Color equals color dot purple. That'll be fun. Okay, so then down here I need to add that to my graph. So FAP dot plot T, and I'm going to plot the x momentum of A. So it's A dot P dot X. I can't plot the momentum because that's a vector. And then FBP dot plot T B dot P dot X, and then FTP dot plot is T A dot P dot X plus A dot B dot P dot X. Let's see what happens. Okay. That's pretty nice. That's pretty perfect right there. Now let's check the kinetic energy. So I need to calculate the kinetic energy. One way to do that is p squared over 2m. So let's make another graph. G2 equals graph x title. I can just copy that. Let's just copy this whole thing. So one of the things with Python, WebVPython, the graphic is really great. If you want to make 2 graphs, you can actually assign which graph each curve goes to. But if you do it in order, if I make a graph, anything below that will be in that graph, and I make a new graph, everything below that will be in the new graph. And so that just works out better. So this is just going to be, I'm going to say K. So let's say FAK, FAK, FTK. Now I just need to calculate the calculate the kinetic energy. So down here, I'm going to say Ka is mag p squared over 2m. So mag A dot P squared divided by 2 times A dot M. KB equals mag B dot P squared divided by 2 times B dot M. And then I need to do the total. So let's just copy this again. Oop. Okay, K. Did I use lowercase or capital? I can't remember already. You forget these things. K, capital. So this is going to be KA, KB, and then this is going to be equal to the sum. KA plus KB. Let's run it. I'm having kind of fun with this, you know. And this is, I want to point out how super simple this is. Okay, so we already saw the collision. That's the momentum. Here's the energy. So the purple is the total kinetic energy. And you can see that the kinetic energy is not really conserved, but it's kind of conserved. So during this right here, the total kinetic energy is 1 times 1.8 times 10 to the negative 2. Afterwards, it's the same. It's 1.8 times 10 to the negative 2. So before and after is conserved. But during is not conserved. During this region, the kinetic energy is not conserved. Because if I have that force, there has to be a potential energy, right? So there's some stored potential energy which I didn't calculate because it's a fake force. And that's fine. It's fine, right? It should be fine. So that's why this total kinetic energy decreases, because there's some type of potential energy that's stored. Now over here, I have such a short range force that the potential energy is essentially zero before and after. So it still works pretty well. Now, I'm going to show you one more thing, and then you can have this to play with because it is pretty fun. Let's try a couple things. We have the whole model working. What if I have this is the classic billiard ball where one hits and the other one moves, but what if they're not the same mass? So let's just change mass. Which one is moving? Mass A. So let's change this to twice as massive, and let's see what happens. Okay, so they both end up moving. That's fine. Is momentum conserved? Is kinetic energy conserved? Let's check. So momentum's still conserved, right? There's my total momentum, still constant. It doesn't matter about the potential energy, right? Momentum is conserved with this force, because as long as they're equal and opposite forces, momentum is conserved. And so the red one slows down but keeps moving. The blue one speeds up. Cool. Kinetic energy still works too, right? Nice. So that's pretty cool. Okay. What about this? Let's try something like this. I'm going to keep that mass the same. All I'm going to do is take that mass A and shift it up. So now it's not going to be a one-dimensional collision. It's going to be a two-dimensional collision. So let's just put this up at, let's say, 0.05. So just shift it up a little bit. So now when they collide, that force still pushes away from their center. So it's not going to be in the x direction, just in the x direction. Do you like that? I like that. I like that. That's pretty cool. Now, is momentum conserved? Well, yep. Momentum is conserved. Is kinetic energy conserved? Well, again, kind of. Not during that collision part. Let's check one more thing. If they're different masses, and they're the same mass, and we have an elastic collision, this is kind of an elastic collision. It's not perfectly because of that energy thing right there. So I'm going to put the mass back at 0.1. Run this. I just want to look at it. So one of the things that should happen is that if the mass is the same and they collide, the angle between their final velocities should be 90 degrees. This should be a 90-degree thing. Can we check that? Yes, we can. Here's what we're going to do. We're going to, at the end of the program, we're going to take momentum A and momentum B. Those are those vector directions that they're going in. And I'm going to take the dot product. If the dot product is 0, then they're at 90 degrees. So let's just check that. It'll be fun. Okay, so down here, I'm done with the loop. I've dedented some. I dedented some of my loop. I need to get my left and rights fixed, but so let's just print. Let's calculate the angle. Theta equals. It's going to be equal to the arc cosine. Let's see. So A dot B equals A B cosine theta. So it's going to be the magnitude. It's going to be arc cosine of A dot P mag times mag. Am I doing this right? I feel like I'm making it hard. Let me switch to the paper because okay, so let's see. A dot B equals A B cosine theta. So no, I got it wrong. Cosine theta is A dot B over A B. So theta is going to be the inverse cosine of A dot B over the magnitude of A times B. Okay, I did do that backwards. Good thing I wrote it down. Sometimes you just got to take a break and write things down. So this is going to be A dot B. It's inverse cosine of A dot B. So dot product is built in A dot P comma A dot B. That's the dot product. Divided by mag A dot P times mag B dot P. And that will give me my angle in radians. Let's multiply that by 180 divided by pi. Print theta equals theta degrees. So this should be 90, I hope. And then we'll run it one more time with a different, got mad. Missing a right parentheses. Okay, I see you. Thanks for catching me on that one. Cosine A dot B. Oh, I didn't. Maybe. Yep. I wasn't really planning on doing that, so I feel like I might have made a mistake. But okay, so it's running. It won't print until it's done. Evaluating an object T dot X. Ooh, really making a mistake here, huh? B dot P, A dot. Oh, the B. Wow. I really wasn't planning for that, and I just threw it at the end, and that really threw me off. So that happens. It's cool. I mean, how many of you are going to make it to the end of the video anyway? And if you are here, I know who you are. And I see you. All right, there you go. So it worked. Let's just try put it back at a larger mass again and just see what happens where it's not 90 degrees. I should make this run faster. See, that does not look like 90 degrees. And in fact, 66 degrees. Okay. So, but again, super simple collision. Momentum's conserved. As long as that force is the same, you can make whatever force you want, try different things, and have fun with that. I will add one homework assignment. I tried to make a force that was both repulsive to push them apart when they collided, but also attractive so they would stick together. So if they got too close, there was an attractive force, but it ended up blowing up all the time. There's another way to make things stick together, and I'll show you that in another video, but this is good. And I will give you a link to this code down below. Have fun with it. Talk to you later.